In this video, we're going to talk about expected value. Let's talk briefly about notation. In chapter 5, we're going to write P of x rather than PR of x for probability. And the reason for the switch is just that the problems for chapter 5 are taken from a different textbook than what we were using for chapters 1 through 4. So there's a slight shift in notation there. So you see that shift in section 5.1 and 5.2. So let's start by defining a random variable. We're usually going to use the symbol capital X for a random variable. What a random variable does is it assigns a number to each outcome in the sample space. So let's say that 3 coins are flipped, and our random variable X is going to represent the number of heads that appear in those 3 flips. We want to find the probability distribution of X. So what we're aiming for is to make a table that looks like this. We're going to list our different X values, and we're going to list our different probabilities that go with each of those X values. But in order to get to that point, we're going to have to do a little bit of intermediate work. So let's set up a table that looks like this. We'll talk about our different X values. Then we can give a description of what each X value represents. Once we've done that, then we can count the number of outcomes that go with each X value. And once we've got that, that will lead us into calculating the probabilities. So let's first focus on these X values here, figure out what numbers should go in this first column. So what X represents is the number of heads that appear in these 3 coin tosses. So we could have 0 heads, we could have 1 head, could have 2 heads, or 3 heads. So those are different options for X. Now let's see if we can write a description for each one. So in the first row, if the number of heads is 0, then that means we must have had the toss or the sequence tails, tails, tails. But for X equal 1, there's actually more than one way for that to happen. If we get 1 head, we could have heads, tails, 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 heads, tails, or tails, tails, heads. So for X equals 0, there's just one possible outcome, but for X equal 1, there are 3 outcomes. So we're going to try to figure out the number of outcomes for the other 2 X values. If X is 2, let's think about all the ways we can get 2 heads. Heads, heads, tails, heads, tails, heads, and tails, heads, heads. So that's 3 outcomes. And for X equal 3, 3 heads, just one way to do that, heads, heads, heads. So it's these number of outcomes here that we really care about. We're going to be able to just add up all of these outcomes. We add them up, we get 8. And then the way we figure out our probabilities is we just take our number of outcomes and divide by the total number of outcomes in the sample space. So we'll do things like 1 over 8, 3 out of 8, 3 out of 8, and 1 out of 8. So if you want a cleaner version of the probability distribution, usually the way that we'll give the answer is we'll just write down the different X values. So 0, 1, 2, 3. And then beside that, we'll write the probabilities that go with those. And so filling in our probabilities, 1 out of 8, 3 out of 8, 3 out of 8, 1 out of 8. And there we have our probability distribution for this random variable X, which represents the number of heads in 3 coin tosses. Now, if we wanted a visualization of our random variable X, we can draw what's called a histogram. Basically, that's just a fancy word for a bar chart when your variable is numerical. And so we can plot our different X values along our horizontal axis, and we can plot our different probabilities along the vertical axis. So thinking about our probabilities, we could go up in increments of 1 over 8. And thinking about our X values, we just want to plot our X values 0, 1, 2, and 3. So we'll plot those like that, and then we'll put a bar over each of these X values. So the bar for 0 should be centered at 0 and just go up to 1 over 8. And then the bar for 1 and 2 go up to 3 over 8 like that. And then the bar for 3 over 3 comes out to 1 over 8. So there we've got a visualization of the different X values that are possible and the probabilities that go with each of those X values. So that's a great visual way to understand a random variable. So now we're going to define the expected value of a random variable. It is the theoretical average if the experiment were repeated infinitely many times. So remember what a random variable is it's just a number associated with each outcome of an experiment. So you do an experiment, something happens, you get an X value, and if you record those X values and you start to average them, then you're getting a sense of what your expected value looks like. So theoretically, the expected value is averaged over infinitely many experiments. Okay, let's see a formula for expected value, and then we will do some examples. So the notation that we're going to use for expected value, we're going to write E of X like that. And the way the formula works, you take your first X value, multiply it by its probability. You take your second X value, multiply it by its probability, and you're just summing up terms that look like this. So depending how many possible values you've got for X, you'd have a certain number of terms in the sum. I'm just going to write plus ... and then you take your last X value and multiply by its probability. So that's our notation for expected value, and that's our formula for calculating it. So your expected value is like a weighted average of the different X values where the probabilities are giving weights to the different X values. So let's see just a very quick example of an expected value. So suppose X is a dice roll, or a roll of a die. So you've got a die and X is just going to represent whatever number comes up on your die. If we were asked to find the expected value of X, then what we would need to do is build a little probability distribution, listing the different possibilities for X and listing the probabilities that go with those different X values. So assuming that this is a fair die, your probability would be 1 out of 6 for each of the different rolls. Then we would use our formula for expected value that says to get your E of X, you're just taking each X value, multiplying by its probability, and doing a sum like that. So we'd have X1 times P1 plus X2 times P2. And since there are 6 different possible values for X, we'd have 6 different terms in that sum. So if we actually worked out what that sum looks like, we'd say E of X is 1 times 1 over 6 plus 2 times 1 over 6. Keep adding up things like that till you get to 6 times 1 over 6. And if you type that whole thing into your calculator, you'd get 3.5. So that gives us a sense of the average dice roll. So let's say a box contains 9 $5 bills and 6 $10 bills. You pay $8 and you draw a bill from the box. We're going to let X represent your net winnings, and we're going to find the expected value of X. Well, really a two-part problem. The first thing we need to do is find the probability distribution of X. So we need to build a little table that looks like this, figure out our different X values and the probabilities that go with those. And once we've got that, then we can think about using our expected value formula to find E of X. So let's work on our probability distribution first. Okay, it's important to pay attention to how X is defined in the problem. So we're told that X is our net winnings. When we say net winnings, that means how much you won minus how much you paid to play the game. So it's how much you're left with after the experiment is done. So let's think about what the two things that can happen are. When we go into this box and we draw a bill, we could either get the $5 bill or we could get the $10 bill. So let's see if we can figure out the X values that go with those. Remember that we paid $8 to play this game. So if we were in the first scenario and we got the $5 bill, then our net winnings would be 5 minus 8 because we paid $8 to play. So that would be -3. So that's our net winnings measured in dollars. Whereas if we were lucky enough to get the $10 bill, then we'd have the $10 minus the $8 that we paid to play. So 10 minus 8 would be +2. Okay, so in that scenario, we have net winnings of $2. Now we need to find the probabilities that go with these. So it might help just to have a visual here. So you've got this box. In there, you've got some $5 bills and you've got some $10 bills. There are 9 $5 bills and 6 $10 bills. So that means there are 15 bills in total in the box. Your probability of actually getting a $5 bill would be 9 out of 15. Probability of getting a $10 bill would be 6 out of 15. So there we go. We've successfully built our probability distribution for X. And now the question is asking us to find the expected value. So if you said this in words, this would be the expected net winnings, because X is representing your net winnings. And if you take the expected value of X, then you're getting your expected net winnings. So this is boiling the experiment down to an average outcome so that we can say, on average, how good or bad is this experiment for us? So what we're supposed to do is take each of our X values and multiply by the associated probability and just add those up. So we're going to go -3 times 9 over 15 plus, and then we're going to take our next X value, 2, multiplied by its probability. And then we can type that whole thing into our calculator, and that comes out to -1. And E of X is your expected net winnings. So if we put this into words, we would say we expect to lose $1 on average. So the fact that this number is negative is telling us that we're expecting a loss. If we saw a positive number coming out of this, then we would have an expected gain. But in this case, this is not an experiment that we should really want to play, as we expect to lose money by doing this. And to make this even more clear, I'm going to say we expect to lose $1 on average each time we play. So if we play once, we expect to lose $1. If the game gets reset, and again, we start off with 9 $5 bills and 6 $10 bills, we do it again, we expect to lose another $1. So if you keep playing, you expect to lose more and more money. So let's say we insure a used car worth $4,000 against theft for 1 year by paying a premium of $112. Let's say the probability of theft is 1.3%. We're going to let X represent your net gain in dollars, and we're going to find E of X. Okay, so using our new notation for chapter 5, we could have written probability like this. Probability of theft is 1.3%. Doesn't really matter whether you use the PR notation or the P notation. So the way we should start off these problems is by building a probability distribution for whatever our variable is. In this case, X is our net gain in dollars. So we're going to try to make a table that describes the different X values and the different probabilities that go with those X values. So let's think about what the two scenarios are. Well, if you're insuring a car against theft, then either the car gets stolen or it does not get stolen. Those are the two situations. So there are going to be 2 rows to fill in the table. Now, an assumption in the problem is that your insurance is covering the entire cost of the car. It's not really stated in the problem, so we're just going to assume that the insurance is for the full $4,000. Okay, so let's think about our net gain in each scenario. So the net gain on the insurance policy. Okay, if the car is stolen, then you receive $4,000 from your insurance company, but remember that you had to pay a premium of $112 in order to get that policy. So you'd actually have $4,000 minus $112 at the end of the year if your car is stolen. So if we do that subtraction, $3,888 is your net gain in dollars if your car is stolen. Now, if your car is not stolen, then you don't receive any money from the insurance company, but you did have to pay your premium. So it's minus $112. You're just $112 out of pocket because you paid for your insurance. Now let's see if we can figure out the probabilities that go with these. We were told in the question, probability of theft, 1.3%. So if we turn that into a decimal, 0.013. So that's our probability that we're in this top situation here where the car is stolen. And to get the probability of the car not being stolen, we're just going to go 1 minus our other probability. So if we put that into our calculator, that's 0.987. Okay, so now we know our probabilities of the car being stolen or not stolen, and we know what our net gain in dollars from our insurance policy is going to be in each of those 2 situations. So the question is asking us to find the expected value. So if you said this in words, it would be your expected net gain from your insurance policy. So this part here, net gain from your insurance policy, is X. And if you put the word expected in front of that, then you're asking for the expected value of X, which we write E of X. So expected net gain from your insurance policy in symbols, E of x. And the way we actually calculate that, let's take each of our x values and multiply by the probability. So you got your 3,888 times 0.013 plus adding on negative 112 times 0.987. And we can type that whole thing into our calculator. So that comes out to negative 60. So if we think units here, this was our expected net gain from our insurance policy measured in dollars. So if we write this up in words, we would say we expect to lose $60 on average. And this is over a 1-year policy, so we could say each year. So that's the bad news. We expect to lose $60 on average each year. But the good news is that the insurance protects us against a large loss. So this is generally why insurance is a very good thing, as long as your premium is not too high. Let's say a shipment contains 10 good and 5 defective items. We're going to choose 3 items randomly from the shipment, and we're going to let X represent the number of good items chosen. What we want to do is find E of X. So again, with all of these E of X or expected value problems, we want to start by building a table that looks like this. We need to figure out what our different X values are and what our different probabilities are. And sometimes in more complicated problems, we have to do a bigger table, like what we did in the first example. So think back to the coin problem at the beginning of this video. And we said, well, if it seems too difficult to calculate the probabilities off the top of your head, then what you can do is give a description of what each X value represents. And then from there, count your number of outcomes and get your probabilities from there. So let's see if this method works better for this problem. So what I'm going to do over on the side is just sort of draw a picture of this box. We've got good items and we've got defective items. So 10 good and 5 defective. And what we're doing is we're choosing 3 items from this box. So just to sort of show you a typical outcome, maybe you could choose 2 good ones and 1 defective one. That's one thing you could do, or you could choose 3 good items, etc. So there are a few different scenarios. Well, if we're choosing 3 items in total, and X is the number of good items chosen, then X could be 0, 1, 2, or 3. Since we're only choosing 3 items, we can't end up with more than 3 good items, but we could end up with as few as 0 good items. Okay, so I think I'll write X equals number of good, just so we know what we're talking about here. And let's start off with this first scenario where X equals 0 and write a description of what we get. So if we end up with 0 good items, that's the same thing as saying 3 defective. And let's think how many ways there are to do that. So if we look up at our box, there are 5 defective items in the box and we need to choose 3 of them. So it's going to be 5C3 is the number of outcomes. Okay, if we move on to the next situation, we get 1 good. That's an incomplete description right now. Full description would be 1 good and 2 defective because we're choosing 3 items in total. And then once we say it that way, then we can use our counting technique from chapter 3 to figure out how many outcomes there would be. So we have to choose 1 good item from the 10 good items, 10C1. The and is going to prompt us to multiply, and then we need to choose 2 defective from the 5 defective items in our box. So that would be 5C2 ways to do that. So we're just going to continue through the rows of this table. Now we're going to talk about 2 good items. So right now that's an incomplete description. The full description would be 2 good and 1 defective. And let's count the number of ways. So from the 10 good items, choose 2, and prompts us to multiply. And then from the 5 defective items, choose 1. Okay, so we're making some progress here. Last row of the table, 3 good items. So you could either say 3 good, that is a complete description of what we're getting, or you could say 3 good and 0 defective. But in fact, this part here is not going to affect your number of outcomes, so you don't really need to say that. You can just say 3 good, 10, choose 3 ways to do that. So in order to make things a bit easier for ourselves, let's create numerical values here using our calculator. So 5C3 is 10. 10C1 times 5C2 is 100. 10C2 times 5C1 is 225 if you do that on your calculator. And then 10C3 is 120. And to get our probabilities, what we're going to do is just add up these numbers and then we'll divide by the total number of outcomes. Our total number of outcomes is 455. And we can create our probabilities just by taking each number of outcomes and dividing by our total. So we get things like 10 over 455. So now we've got all the information we need, which is we've got our X values and we've got our probabilities. So at this point, those are the only two columns that we care about. So I'll just keep those highlighted. And remember, the question was to find E of X. So let's break out our formula for E of X. What we're supposed to do is take each X value and multiply it by its probability. So we're going to go 0 times 10 over 455, and we're just going to add up all the terms like that. So if you put this into your calculator, this is very satisfying, comes out to a very nice round number, comes out to 2. X was the number of good items that we selected, and when we say E of X, then you're saying what is the expected number of good items. So the expected number of good items is 2. We expect 2 good items on average. So it gives us a sense of what the average outcome of the experiment is going to be. So one more definition for this section, we're going to say that a game is fair if the expected net winnings is 0. So for example, you could say a game in a casino is fair if you're equally happy to be the person playing the game or to be the casino itself. Now, in practice, games in casinos are never fair, but we'll say a game in the real world is fair if you're equally happy to be either party in the game. Let's say you pay $1 to roll a die. We'll assume this is a fair die. If you roll a 1 or a 6, you win $5. Otherwise, you must pay K more dollars in addition to the $1 that you already paid. We want to find the value of K so that the game is fair. So the plan for the problem is that we're going to build a table that looks like this. We'll list our different X values and our different probabilities. So if we're talking about whether or not a game is fair, it's your net winnings that you're interested in. So let's let X be the net winnings. So let's think about the two scenarios here. So you could have a winning scenario where you roll a 1 or a 6, or you could have a losing scenario. I'll just say otherwise. If you roll anything else, you're in a losing scenario. So let's see if we can figure out our net winnings in each case. That is how much money we're walking away with after this experiment is done. Well, if you roll a 1 or a 6, you win $5. But remember that you paid $1 to play. So it's really your winnings minus however much you paid to play. 5 minus 1 means a $4 profit, if you want to say it that way. Otherwise, we're told you must pay K more dollars, where K is some unknown number. Okay, so we paid $1 to play, and now we have to pay K more dollars. So it's minus 1, the dollar that we had to pay at the beginning of the game, and then minus K because we're paying K more dollars. So each time you're paying something, it's a negative winning. Now let's think about the probabilities of these two scenarios. So it comes down to the roll of the die. If you roll a 1 or a 6, your probability of doing that 2 ways out of 6. Probability of getting any roll other than a 1 or a 6 would just be 1 minus the 2 out of 6. So let's make that 4 out of 6. So if we have a fair game, by definition, the expected net winnings should be 0. And if we translate that into symbols, since X is our net winnings, the expected net winnings is the symbol E of X. So now we're just going to plug in on the left side what the actual expected value is. So we're going to take each of our X values, multiply it by its probability. So 4 times 2 over 6, plus then we have to multiply -1 minus K times 4 out of 6. And we want this whole thing to equal 0. So what we're doing is we're trying to find the k value that makes the game fair. And that's going to come down to just solving this equation. So first thing I would want to do here is just get rid of the fractions. So let's multiply both sides by 6. Our first term here is really like 8 over 6. So after we've done the multiplication, we're going to end up with 8. And for the second term, if we multiply by 6, we're going to end up with -1 minus k times 4 equals 0. So let's expand this out. We've got 8 minus 4 minus 4k equals 0. So we got 4 equals 4k. In other words, k equals 1. So the value of k that makes the game fair is 1. So that's our video on expected value. Thanks for watching.